Okay, let's think about an example. The first example is a regulation. Let's consider that FTC is Freight Trade Commission, maybe committee, it's a government agency that regulates whether the information is correctly delivered, correctly labeled on the products. So FTC periodically tests if the label information is correct or not. And suppose that there is a coffee labeled as 3 pounds. So I suppose that you are the agent in this agency, and you are looking into a coffee product which is labeled as 3 pounds. It has to contain 3 pounds, and if the content is smaller than 3 pounds, the company should be punished, maybe penalized, or maybe some actions will be taken. How so? You are checking whether the content is lower than 3 pounds or not. However, if even if the label information is 3 pounds, but if the company is giving out more than 3 pounds, do we have to punish that? I think no. So, if the company is underselling their product, that is unfortunate, but we are not going to punish them. So, if they are selling actually 3.5 pounds at the price of 3 pounds, there is no point of regulation, punishment in that situation. So, we don't care if the content is more than the label information. The problem arises only when the content is less than the label information. So our hypothesis will be formulated in this way. Your null hypothesis is that the mean population is 3 pounds, but alternative hypothesis is less than 3 pounds. The company is cheating. So as I said, simply you don't care if the content is more than 3 pounds, or you may believe that it would not happen. It would never happen. There would be no company who intentionally does that. So either way does not matter. As I said, I don't care. Simply we are not interested in that side. So we are only interested in the lower tail. So we are testing on the lower tail, smaller side. In other words, we are going to punish if it's too small. If the data shows the mean is too small, then we are going to punish. That's one tail test. Now let's think about data. Suppose that you inspect 100 randomly chosen products, coffee products, and you found that you measured their content amount. You found that the sample mean content was 2.82 pounds, which is smaller than the label information, 3 pounds. The label says 3 pounds, but you found 2.82. Now you have to think about this. The difference could be simple like measurement error, or maybe it could happen. The measurement error or just manufacturing error could happen, or simply the company is cheating. Company is making the content a little bit smaller than it has to be. It has to contain. So there are two possibilities. You have to make decision. What's the case? Which is the case? Anyhow, in the end, we cannot tell. We don't know the truth, but still we have to make the decision, and we are going to use the framework we studied in the previous chapter. Standard deviation equals to 1. The first thing you have to do here is to calculate the t-statistic. T-statistic equals the difference. 2.82 is the sample mean, what the data tell you, and mu0 is your hypothesis, what your hypothesis tells you. And so the data tells you that the mean is 2.82. Your hypothesis is 3. So their difference is 2.82 minus 3 divided by 1 over square root of 100. Then it's easy to see that the t-statistic is minus 1.8, which means the sample mean is 1.8 standard error below what it has to be, right? The difference is 1.8 standard error away from the from 0. And p-value is calculated from the t-statistic. As I said, we only care about lower side, lower tail, so this is the p-value. I don't care, I don't include the positive side. Positive side is not considered at all. So p-value is calculated this way. Simply, it's a CDF, cumulative probability of standard normal distribution at minus 1.8 is 3.593%. Because this is the direction, this direction is the direction we are going to reject the null hypothesis. Positive errors don't matter. I don't care. So anyhow, that's it. So there is no difference, but the only difference is to ignore the one of the two sides. And anyhow, then from these, consider you are using 5% significance level. Are you going to reject it? Can you reject the null hypothesis or not? Use the same decision rule. You may use p-value. We have p-value, so you can think about the p-value. Decision rule. 3, 2, 1. The answer is you are going to reject the null hypothesis. The answer is reject. Because remember, we compare the significance level and the p-value. If the p-value, so significance level 5% means you are going to reject 5% most suspicious companies, right? 5%, top 5% will be rejected, but your observation is within 3.5%. So it's within top 5%, it has to be rejected. The answer is rejection. So reject because it's smaller than alpha. However, let's think about this case. If it was a two-tail test like this, so now the alternative hypothesis is a negation of equality. If you think this way, the p-value has to include lower tail plus upper tail. Both lower tail and the upper tail must be included in the p-value. When you rank from the most suspicious case, you have to consider the bottom and the top at the same time. They are higher ranked at the same time, so overall ranking goes down. Anyhow, so because of this, always they are symmetric, so the p-value in this case would be 7.1, which is exactly twice double the p-value from one-tail test. So when you change one-tail test to two-tail test, p-value increases, the p-value will be doubled because you have to consider another tail which is exactly symmetric, exactly the same value probability to the other tail probability. So the p-value must be doubled. In this case, the decision is now different. You cannot reject H0 because p-value is 7%, which is greater than 5%. Right? Right. So this is the major difference between one-tail test and two-tail test. So remember, the point is the intuition was that I am going to reject top alpha probability, and when you have one tail, you just rank just on one tail. You consider one tail outcomes, but when you have two tails, you have to put both outcomes into the same 5%. So as a result, you are going to reject more in the one tail test. So even if an outcome is rejected in one tail, but it may not be rejected in two tails. All right. So the t statistic is the same. So that was the p-value approach. Now let's think about the t-statistic approach. T-statistic itself is the same, but you have to change their cutoffs, the thresholds, corresponding to according to this decision rule. P-value decision rule changed because you considered only one side. So the threshold for the t-statistic must accommodate that. So the idea is AH0, the null hypothesis test, null hypothesis is rejected if p-value is alpha, and p-value is this probability. So we are looking for the cutoff will be the value that makes this p-value equals to alpha. So when it becomes equality, that's the cutoff, right? If you change it to equality, that equality will provide the cutoff value. Simply, it is these values. That means the idea is actually easier. When you reject 10%, so alpha is 10%, then you are rejecting top 10% from the bottom or from the top, say, like one tail. So you are rejecting 10%. So the cutoff is just 10% from the bottom or from the top. Previously, it was different. Anyhow, let me continue. If you reject 1%, alpha is 1%, then you just need to take bottom 1% or top 1%. So we have a different thresholds: 1.28, 1.64, 2.33, which is coming from these values, right? So 90% means top 10%, 95% means top 5%, 99% means top 1%. So because the rejection happens only on one side, it's actually easier to understand what's going on. So from the standard normal distribution, find the rank, the value from top 10%, top 5%, top 1%. That's the cutoff. Okay, then suppose that there is another coffee product with 3 pounds label, and now for that product you found that the t statistic is minus 1.5. Then find the significance levels that rejects the null hypothesis. When t statistic was 1.5, when will it be rejected? I'm going to stop the video now, and please continue in the next video after answering this. See you later.